Okay, welcome to the video for Calculus 2. This is for February 3rd, and lots of people missed class today either because of illness or because of weather. So I'm creating a video of the lecture that was held in class that'll help you get caught up. Unfortunately, I could not get Scientific Workplace to give me a black background, and I don't have a pen pad, so I can't write freehand. You're just going to have to deal with a white background, and I apologize for that. I am also going to make it available on the web page, which it'll be on the web page by the time you can view this video, a PDF document of what we're going to create here. And what we're going to talk about are inverse trigonometric functions. Now, the reason inverse trigonometric functions are powerful in calculus is mostly because of integrals. But to get to the integrals, we have to start with the derivative. So to start with that derivative, I need to figure out what the derivative of our inverse trig functions is, or I guess the derivatives are, to keep my tenses correct. Now, there's several inverse trigonometric functions. We're going to mainly deal with two of them, and I first want to give a little bit of a review on what those trig functions are. Okay, so I'm going to switch to math mode here. And the first one is inverse sine. And I'm not in math mode. There we go. Okay. So if I have inverse sine of x equals y, then that means that sine of y is equal to x. Okay, and whenever you got this different colored text, that means I'm entering mathematics here. Okay, so for example, if I wanted to have inverse sine of 1, that's going to be some number y so that sine of y is 1. Well, it turns out there's more than one possibility. Okay, now the one that's probably going to be most common for people to think of is pi over 2. The sine of pi over 2 is 1. But it could also be 3 pi over 2, or excuse me, 5 pi over 2. It would not be 3 pi over 2. 3 pi over 2 has a sine of negative 1. So we could have or 5 pi over 2. Because that also has a sine of 1. If you take sine of 5 pi over 2, you get 1. So we're going to have to do a little bit of work to get this inverse trig function to actually be a function. As it is right now, we have multiple possible outputs for it. And the way we're going to do that is we're just going to restrict the domain and the range of the inverse trig function so that it is indeed an inverse trig function. So the first one is inverse sine, and inverse sine and by the way, pretty much any trig class is going to be talking about these things, but you might not remember. It might have been a little while. Inverse sine is going to have domain equal to the closed interval from -1 to 1. Okay, and that's because what we input into inverse sine is a ratio. That's the opposite over the hypotenuse. Remember, with sine, the input's the angle and the output's opposite over hypotenuse, if you're viewing these with the right triangle. But for inverse sine, we switch the domain and the range, the outputs and the inputs, so that the inputs are actually the ratios, and those have to range between -1 and 1. And then the range of inverse sine, we need to restrict this so that multiple outputs don't happen. Okay, and sine of negative pi over 2 is -1, sine of pi over 2 is 1, so that catches the entire range of possibilities for sine. So if we use angles from negative pi over 2 to pi over 2, then x ranges over our entire domain from -1 to 1. So that's going to end up working for us. So we'll have the interval from negative pi over 2 to pi over 2. I'll just copy that one over here. And that works for inverse sine. For our other trig functions, though, inverse trig functions, it'll be a little bit different. Let's consider inverse cosine. So first we'll talk about the domain of inverse cosine. Now this is the inverse cosine function, so the domain is going to be equal to the range of cosine. Well, cosine, like sine, can take values anywhere between -1 and 1. So the domain is going to be -1 to 1 for inverse cosine. Now what's the range? Well, we won't be able to use -pi/2 to pi/2. Okay, because cosine of -pi/2 is 0, cosine of pi/2 is 0, and everywhere in between cosine is positive. So we would never get the negative, we'd never get cosine equal to a negative number between these two angles. So instead, what we're going to do is we're going to take our range to be 0 to pi. And that works well because the cosine of 0 is 1, the cosine of pi is -1, and by taking x values everywhere between -1 and 1, you'll get outputs of angles between 0 and pi. So the range here is going to be 0 to pi. And we'll include those endpoints so it is indeed a closed interval. Okay, and finally we're going to talk about inverse tangent. And yes, I know that I said that we're only going to have two important inverse trig functions, and that was not a lie. That is true, but we're going to start off with 3, and we'll along the way see why we only really need to think about 2 of them. Now tangent is a little bit of a different animal. Let's graph tangent. So if I have tangent of x, and I'm going to go up to 2D plot. Tangent of x looks like this. Okay, it's got an S-curve and it has vertical asymptotes every once in a while. Now where are these vertical asymptotes at? Well, a vertical asymptote for tangent occurs when we have cosine equal to 0, because tangent sine divided by cosine, and vertical asymptotes are usually created when we divide by 0. So these vertical asymptotes are when cosine is 0. And cosine is 0 at pi/2, and -pi/2, and -3pi/2, and 3pi/2, etc. Now, the domain of inverse tangent is going to be the range of tangent, all the y values that are assumed. Because we have a vertical asymptote here, it doesn't matter how far my graph goes up. Let's see, I could change the properties so that it went up higher. Maybe my y values go from -20 to 20. Okay, tangent's still going to go up that high. See how it keeps going? Even if I change to 200. Okay, it's going to look pretty sharp, look like a weird graph. But tangent still goes up that high, and it ends up going as high as you could ever want. So the output for tangent can be any real number. The range is from -infinity to infinity. So for inverse tangent, that's going to be our domain, the open interval from -infinity to infinity. Now what's the range of inverse tangent? Okay, I need to restrict the range, and remember the range of inverse tangent corresponds to the domain of tangent. I need to restrict it so that I just have one angle corresponding to each ratio. Well, I'm going to go from -pi/2 to pi/2. And this isn't just me saying that. It's standard to go from -pi/2 to pi/2 for the range of inverse tangent. You could go from, say, pi/2 to 3pi/2. However, that would not be standard. You would have problems communicating with people, and it'd just be a little bit more messy. 0 isn't in that interval, and it ends up being nice to have 0 there. Okay, so there's our 3 inverse trig functions. Remember, they're backwards trig functions. Trig functions input angles, output ratios. Inverse trig functions are going to input angles and give you a ratio in the range. Okay, the inverse trig functions are going to input ratios and give you an angle in the range that corresponds to that ratio. Now, of course, this is calculus class, and all we've done so far is talk about trig, so we need to get on to derivatives and antiderivatives. So derivatives of inverse trigonometric functions. And to get these derivatives, we're going to use implicit differentiation. Okay, so first we'll start with inverse sine of x. So I want the derivative of, I'll write that out here. Let's change to text mode. Derivative of inverse sine of x. Can I underline that? No, it doesn't like underline. Okay, let me put stars here, because that's what we're doing. I would underline that if I knew how to. I'm sure there's a way. I just don't want to fiddle around while I'm making this video doing that. Okay, I'm going to use implicit differentiation for my inverse trig functions. And to use implicit differentiation, we need an implicit function. So I'm going to write inverse sine of x, the same definition as we had before. Inverse sine of x is y. Okay, that means that sine of y is equal to x. Okay. So I'm going to take the derivative of both sides of sine of y equals x. Okay, on the left side, the derivative of sine is cosine, and I'm going to treat y as an inside function. I'm taking the derivative with respect to x. Maybe I should have said that. Take the derivative with respect to x of both sides. Okay, so I have an outer function that's sine. I have an inner function that's y. Now I don't have a formula for y, except for inverse sine, but that won't help us in terms of taking the derivative. So when I take the derivative on the inside, I'll just put y prime. So the derivative of sine is cosine, and I get cosine, leave the inside the same, and then multiply by the derivative of y, which we'll just call y prime. And then the derivative of the right-hand side with respect to x is just 1. Okay, so if y is inverse sine of x, then that means the derivative of y is 1 over cosine of y. So y prime is, let's make a fraction here, 1 over cosine of y. Okay, now I'm going to rewrite this in context here. We know that this derivative, or the y prime, is a derivative of inverse sine of x. So let's do that. Sine, inverse sine of x there. And that equals 1 over cosine of y. However, I'm going to go ahead and plug in for y. I know that y is inverse sine of x, so let's just copy and paste. Well, I was supposed to copy there. Copy. Oh, it does not want to paste for me. Let's try this. Let's try 1 divided by cosine of, and then paste it. Yeah, it was a little bit too complicated to put on the bottom of that fraction, I think. And what we're going to do is get a simpler formula for this right here. Now, inverse sine of x is an angle, right? Sine inputs angles and outputs ratios. Inverse sine, however, inputs ratios and outputs angles. So I'm going to call it theta. And I'm going to say let theta equals inverse sine of x. Now the Pythagorean identity tells me that cosine squared theta plus sine squared theta equals 1. And what this is going to allow me to do is get an expression for cosine theta. If I solve this for cosine theta, then the sine squared theta is subtracted over, and I take the square root, need to put a plus or minus there, and I get that cosine theta equals plus or minus the square root Let's see, how do I do square root? Let's see if we can. Not that. Symbol. I don't think that it's in there somewhere. Oh, you know what? I bet my window's just not large enough to be able to see it on the toolbar. Let's leave that symbol cached there. Yes, I think it's on this toolbar, but that toolbar wasn't visible because I couldn't see it. There we go. Okay, so I got plus or minus the square root of 1 minus sine squared theta. And now you get a look at my part of my toolbar here, which I had hidden from the screen. Okay, now we know what theta is. Theta was just inverse sine of x. Now I'm going to rewrite this thing with a more convenient way. Let's see, that should be copy. Well, I'm having trouble with my pasting in Scientific Workplace. I'm going to rewrite this so that that squared is on the outside. Okay, now we're going to work with the sine theta. So let's just put it by itself here. Sine theta is sine of, well, theta is inverse sine of x. So it's sine of inverse sine of x. Now remember, this does not mean 1 over x. So I don't get sine divided by sine of x and I cancel out and get 1. That isn't what this power negative 1 means. It means the inverse function. Specifically, inverse sine inputs the ratio x, and it outputs an angle that has sine equal to x. Okay, so if x were square root of 2 over 2, then inverse sine would be the angle pi over 4. And then we take sine of that angle. Well, sine of pi over 4 is square root of 2 over 2. So we get back to where we started. See, it doesn't matter what x is. What we have right here, what theta is an angle that gives us a sine of x. So if we take sine of that angle, we get x. And things simplify really nicely. And I have this formula. Cosine of theta is just equal to plus or minus the square root of 1 minus x squared. Okay. Furthermore, note that theta is an output of inverse sine of x, and if we scroll up here, remember the inverse sine of x had range negative pi over 2 and 2, negative pi over 2 to 2. So theta is in the interval negative pi over 2 to 2. Okay. What that means is cosine cannot be negative. Okay, cosine between negative pi over 2 to pi over 2 is non-negative. Let's graph cosine here, and we see negative pi over 2 is just a little bit to the left of negative 1.5. Pi over 2 is just a little bit to the right of 1.5. See that the y values are all bigger than 0 here. Okay, so cosine is positive. This means I don't have to worry about the plus minus. And I have that, let's see, I'll copy and paste this. Cosine theta is positive square root of 1 minus x squared. Okay, now we're doing a lot of trig here. Let's get back to the calculus. Why were we doing this? Why did we care about cosine theta? We cared about cosine theta because it was on the denominator of our derivative here. Okay, so the derivative of inverse sine of x is 1 over the square root. The square root of 1 minus x squared. Okay, and that is really cool. Notice that we have a trig function over here. We take the derivative. It's an inverse trig function, but still trigonometric. And we get something that doesn't look very trigonometric at all. Okay, so that's going to be our first important derivative, that the derivative of inverse sine of x is 1 divided by the square root of 1 minus x squared. Okay. It turns out we could not get the antiderivative of this. So if you had the integral of 1 over the square root of 1 minus x squared dx, you can use integration by parts, you can try substitution. It just won't work. We have to have this inverse trig function to be able to state the definite or the indefinite integral in closed form. Okay, that was fun. Let's do it again. This time we're going to do the derivative of inverse cosine of x. Let me see, I think I skipped a line there. Yep. Okay, so inverse cosine of x okay, if we let that be equal to y, then that means that cosine of y is equal to x. Okay, and furthermore, it means that y has to be in the interval 0 to pi, which we'll use later on, just like we did up here. Okay, so if we want to take the derivative of inverse cosine, we could use implicit differentiation on this. So that's what I'm going to do. I'm going to take the derivative of both sides of this equation. And yes, this is a little bit of abusive notation. Our derivative was defined for functions, not for equations, but I'm going to say that this means take the derivative of both sides of the equation. So on the left side, the derivative of cosine, that's the outer function, is negative sine. So I have negative sine of y, leave the inside function the same, and then multiply by the derivative of the inside, which is y prime. I'll put a multiply by sign in here. And then on the right side, we just get 1. So if we solve for y prime, we learn that the derivative of the derivative of inverse cosine is negative 1 divided by sine of y. Okay, negative 1 divided by the inverse cosine of x. Now it turns out, negative 1 divided by the sine of the inverse cosine of x. I'll go ahead and put that here. Negative 1 divided by the sine of inverse cosine of x. And I keep getting a little too fast on that 9. Not letting myself hit the shift key. Okay, well, we're going to do the exact same kind of thing as before. We're going to think of inverse cosine of x as an angle, and we often denote angles by theta. So I'll use that here. Theta is going to be inverse cosine of x, and I guess I should tell you what we're doing here. That's not a conclusion, that is a definition. Let theta equal inverse cosine of x. Okay. Well, again, we have our Pythagorean identity that says that cosine squared theta plus sine squared theta is 1. Okay. And what I'm wanting to do is express this sine of theta in a different way. So I'm going to solve this formula for sine theta. That means I subtract the cosine squared theta and take the square root of both sides and put a plus or minus on the right side. And we get that sine theta is equal to plus or minus the square root of 1 minus cosine squared theta. Okay, well, we know what theta is. So let's see. First of all, I want to rewrite that squared. That's a common way to write the squared, but we can also put the squared out here, and that will line up more with how we treat other functions, not just trig functions. Let's see if I can, there we go, got rid of that exponent. What if I can get rid of this one? There we go. And let's see here. Theta is inverse cosine of x. So I'm going to put that in there. And I'll put it in both places. So theta is inverse cosine of x. We'll need to put in parentheses here. And actually both places. Alright, now I've got inverse cosine of x. That is an angle. Remember, inverse cosine, inputs ratios, outputs angles. That is an angle that has cosine equal to x. Well, if we take cosine of that angle, sure enough, we get x. These are inverse functions. I have cosine and the inverse function of cosine. So if I compose them, the output is just what we started with, the input. This whole thing is just x. And I have this square root of 1 minus x squared with a plus or minus out front. Okay, so let's put that down here. I can just replace all of this with x. Okay, and I still have this pesky plus or minus there. Well, it turns out we can get rid of that. We know that inverse cosine of x, okay, is in the interval what? Well, if I scroll up here, how do we define inverse cosine? We defined it so that its output was between 0 and pi. Okay. Now what happens if I take sine of an angle between 0 and pi? Well, let's see. I'll type sine theta down here and we'll graph it. Alright, there's sine theta. Pi is a little bit past 3, so that's where we have this x-intercept. Between 0 and pi, sine is non-negative. Okay, I can't necessarily say positive because I am including these endpoints where it's 0, and 0 is not a positive number, but I can certainly say non-negative. It doesn't get negative in here, so I can take the negative off of that plus minus. And we get that that sine of the inverse cosine of x is a square root of 1 minus x squared. Okay, now we're trying to take the derivative of inverse cosine, and let's see, what do we have here? We have that right here. So y prime, y was inverse cosine, so we got the derivative of y is the derivative of inverse cosine. Let's go ahead and put that there, d dx of inverse cosine. Okay. That's negative 1 divided by sine of inverse cosine of x. So it's negative 1 divided by the square root of 1 minus x squared. Okay, and there's our derivative for inverse cosine. Now it turns out this one doesn't get used very often because, let's look at the one we just calculated up here. The derivative of inverse sine is 1 over the square root of 1 minus x squared. The derivative of inverse cosine is negative 1 over 1 minus x squared. So in terms of integrals, you can use either of these. If you have the integral of 1 over square root of 1 minus x squared, you could say that's negative inverse cosine of x. If you have the integral of negative 1 over square root of 1 minus x squared dx, you could say that's a negative inverse sine of x plus c. Okay, I should have put plus c when I was talking about the other one too. So it turns out these are so similar that we usually only work with this one. Okay, and that's similar to modeling with trigonometric functions. If you're trying to model oscillatory behavior, then you can either use sine or cosine because they're really just horizontal shifts of each other. Okay, the last derivative we're going to do is the derivative of tangent of x. Whoops. Excuse me, inverse tangent of x. And remember that inverse tangent of x, if we let that be y, that means that tangent of y is equal to x. Okay, so we're going to take the derivative of both sides of that. Use our implicit differentiation skills. And what do we get? Well, on the left side we have the derivative of tangent, and the derivative of tangent is just secant squared. So I have secant squared of x, or excuse me, secant squared of y times the derivative of the inside, so that's times y prime, equals the derivative of x on the right side is 1. Okay, so y prime is 1 divided by secant squared of y. And similarly to above, we're going to get a Pythagorean theorem or Pythagorean identity and be able to simplify this down a little bit. Okay, so secant squared of y, I'm going to write that as secant of y squared, so I'll have a squared on the outside here. And then secant of y, well, I know what y is, I'm going to write it as a different formula. I'm going to write it as the inverse tangent of x. So we'll have tangent negative 1 of x. So I have 1 divided by the secant of inverse tangent of x squared. Okay, so our Pythagorean identity that we used above was that cosine squared plus sine squared is equal to 1 for any angle. And we are going to have theta be the angle that we get as an output of tangent. So we get theta is inverse tangent of x. Now tangent doesn't show up here, so that's not useful. What we're going to do is we're going to take both sides of this equation and divide by cosine squared. And the reason I want to divide by cosine squared is this term right here. If I take sine squared and divide by cosine squared, that'll give me tangent squared. And then I have an identity that involves tangent. So I'm going to take each of these terms and divide by cosine squared. Since I'm dividing the left side and the right side by the same thing, I'll still get an equation that's true. Now cosine squared divided by cosine squared is just 1. Okay. Sine squared divided by cosine squared is tangent squared. And my angle is theta. And then 1 divided by cosine squared is secant squared of theta. Okay, and nicely, our identity also included secant. Okay, our identity also included secant. So what we have here is secant of theta. So I'm going to solve for secant of theta, and I just do that by taking the square root of both sides and stick a plus or minus on one side. So secant of theta is equal to the positive or the negative of the square root of 1 plus tangent squared theta. In that green box, I can get rid of that. Okay, now I know what theta is, so I can rewrite this, so it'll be a little bit more useful to us. Secant of theta, well, that is secant of inverse tangent of x. That's equal to plus or minus the square root of 1 plus tangent squared theta. Well, that is 1 plus... Okay, I'm going to have tangent theta squared, and theta, remember, is inverse tangent of x, so I'm going to put that in for theta. Okay, so this is just rewriting what I have above by inserting inverse tangent of x in for theta. Okay, and once again, this works out real nice. Remember, the inverse tangent of x, this inputs a ratio. It's sine over cosine, or opposite over adjacent if you're dealing with a right triangle. It inputs a ratio and outputs an angle. And that angle is an angle that gives you tangent equal to x. Well, if we take tangent of that angle, we get x. That's how that angle is defined. So this whole thing just simplifies down to x squared. And we have the secant of inverse tangent of x is plus or minus the square root of 1 plus x squared. Okay, now we actually could at this point go through and convince ourselves that the plus or minus could go away, but it turns out you don't have to for this case, so I'm not going to do that. Instead, I'm going to go back here. We got y prime, that means the derivative of y, so we're dealing with the derivative of inverse tangent. So we got the derivative of inverse tangent of x, which is, by the way, also called arctangent in some contexts. That's y prime. That's equal to 1 divided by secant of inverse tangent of x squared. So in other words, we have this expression squared. Okay, and notice that I got a plus or minus here, but it gets squared, so it goes away. I got a square root, so it goes away. And we have that the derivative of the inverse tangent function is just 1 divided by 1 plus x squared. Okay, 1 divided by 1 plus x squared. If you want to write that as a fraction, then that's 1 over 1 plus x squared. Alright, and there's the other inverse trigonometric derivative that is going to be useful to us. Okay, so we got that the derivative of inverse tangent is 1 over 1 plus x squared. Again, that's really cool. We're taking the derivative of inverse tangent, or an inverse trig function, and we just get a rational function here. And then the derivative of inverse sine is 1 divided by the square root of 1 minus x squared. Okay, so those are a few more tools to put into the calculus tool belt that we all are trying to build up in this course. Okay, so I got a couple of derivative statements there. I also want to state the integrals, and that is that if I have the integral, let's see, where's my integral sign? There it is. The integral of 1 over the square root of 1 minus x squared, okay, dx, we know what that's going to be now. Okay, we know what it's going to be. It's going to be inverse sine of x. So I'm going to hit evaluate there. I think it might say arc sine. I think Scientific Workplace might use arc sine. I'm not for sure. I know it doesn't put the plus c on there. Yeah, it uses arc sine, which, as I said, is just another way to say inverse sine. I'm going to put inverse sine here to be consistent. I've also been putting parentheses on most of the time. I noticed a few times that I didn't. And then what happens if we take the integral of 1 over 1 plus x squared? Well, you should know what's going to happen. Okay, that is the derivative of inverse tangent. So if I hit evaluate up here, we indeed get arctangent. Now, wait a second. This is an arctangent. This is arctangent of x minus pi over 2. Huh, that's strange. Okay, this is not incorrect. Remember that Scientific Workplace is not putting a plus c on here. Okay, Scientific Workplace is not putting a plus c. So the fact that it added a negative constant doesn't change the answer. And so we should be putting a plus c, and then to be consistent, I'm also going to change this to tangent to the power of negative 1. Okay, so there's the two integrals that we're going to pick up this week and work with. So let's do some examples. Now usually they won't show up quite in that form, but the times that it'll be useful is when I have a number on top, a number here, and some number times x squared, and I do need a minus sign there for this to work. Okay, if I have an x on top, or an x squared, or an x cubed, then we've got some work to do in it. We won't be able to directly apply these. We might not be able to apply these at all, or we might just have to do a little bit of work before we can apply them. Okay, so let me look at my notes here and see what examples I was going to do for you. Okay, the first one, I think we're going to do 3 examples. Yeah, we're going to look at 3 examples here. And the first one is almost direct, but not quite. I'm just going to put one more little thing in here. So I got the integral of 1 over, let's see, I don't know. I'm going to use fractions. I hope you'll be able to see that. And I'll tell you what, when I'm editing this video, I will zoom in on what's going on here. Whoops. The integral of 1 over 1 plus 2x squared dx. Okay, now to do this integral, I want to change it into something that looks like this. Something that looks like my derivative for inverse tangent. Okay, but I've got this extra 2 here. What do I do with that? Well, I'm going to use a trick. Okay, and this is indeed a trick. I'm going to rewrite that same integrand, 1 over 1 plus 2x squared, except to get that 2x squared, I'm going to take the square root of 2, multiply it by x, and then square that product. Okay, so you should convince yourself that these are really the same thing. If I take 2 and multiply by the square of x, do I get the same thing as if I square the product of square root of 2 and x? Okay, and you do, because the square root of 2 squared gives you the 2, and then the x squared gives you the x there. Okay, and what this allows me to do is to do a substitution to get it to look like what we want it to. So I'm going to let u equals the square root of 2 times x. Okay, that implies that du is the square root of 2 times dx. So then dx is du over the square root of 2. Okay, so if I plug back into my integral, let's see, I have that this integral equals I'm going to take this, I'm going to replace the square root of 2 times x with u. Okay, and then the dx will become du over the square root of 2. Okay, and if I pull that 1 over the square root of 2 out, then I have 1 over square root of 2 times the integral of 1 over 1 plus u squared du. There we go. Well, this is just inverse tangent of x. Okay, so this is 1 over the square root of 2 times inverse tangent. Excuse me, that's just inverse tangent of u, not x. And then I got an added constant hanging around there. So if I plug back in for u, let's see, u is equal to square root of 2x. So I have 1 over the square root of 2 times inverse tangent of the square root of 2 times x plus c. Okay. And it should be that when I take the derivative of this, I get the 1 over 1 plus 2x squared. As we saw above, though, sometimes Scientific Workplace will do funky things when it's taking derivatives and antiderivatives. Nevertheless, let's give it a try. Let's copy this expression and ddx it. So we're going to take the derivative of that. Okay, and let's evaluate exactly. And it actually did spit it out in the same form as what we had it in. 1 over 2x squared plus 1. So that was checking to make sure that this answer was correct. Okay, so we see that we can finagle constants around a little bit. And we're going to do another example where we finagle constants around. And this example is going to be the integral of 2 over the square root of 3 minus 4x squared dx. This time, however, I have 3 constants floating around that I need to somehow modify away so that they're not inside the integral anymore, and then I just have 1 over 1 minus x squared, which would be which would have antiderivative inverse sine. Okay, well, the first one's easy. The first step, we just pull a 2 out, right? And then we have what's above there. I'll just copy that integral down, and that'll be a 1. Now I want to get rid of this 3, and to get rid of the 3, what I'm going to do is factor it out. Now, you're not used to being able to factor 3 out of 4, but we can. We just take 4 and we divide it by 3. Okay, so this will be 4/3. I'll write this as a fraction so you know I'm not dividing by the x squared. 4/3. I bet the resolution is going to be horrible when I zoom in on this. Times x squared. Okay, now we can break up that square root. The square root's of a product is the product of the square roots. So I can have the square root of 3 times the square root of 1 minus 4/3 x squared. So let's put a square root of 3 out front. And I'll put a multiply sign in here just to explain a little bit of what's going on. And then that square root of 3 can float out. Okay, so we'll have equals 2 divided by the square root of 3. Okay, and then we have this integral here. Now, the square root of 3 is gone. And now this is a problem very similar to what we had above. What we had above, here we had an extra 2 hanging out by that x squared. Here we have an extra 4/3. So what I'm going to do is put this in parentheses and change the 4/3 into the square root of 4/3. So we got square root, and I'm going to really need to not use a fraction this time. And it'll be clear that that fraction doesn't go on to the x because the square root ends. Let's see, let's get rid of that little annoying green box. Okay, well now I can do a substitution and let's see, u equals the square root of 4/3 times x. Maybe it doesn't like the size. Maybe it has a hard time. There we go. Because that one up there was smaller because it was in a square root and under a 1 in a fraction. Okay, well this means that du is equal to square root of 4/3 times dx. Okay, so dx is du over square root of 4/3. Now, if I have du divided by the square root of 4/3, dividing by the square root of 4/3 is the same as multiplying by the square root of 3/4. So I'm going to do that. I'm going to multiply by the square root of 3/4. That'll end up canceling out for us really nicely. Okay, so now we're going to plug back in to our integral here. So this, let's see, I'll have that this is equal to, we've gotten it down to this point, so I'm going to copy that down here and make my adjustments. This is just u squared, so we'll replace that with u, and this is, let's see, that's dx, so it's a square root of 3 divided by 4 du. Okay, and what can we do here? Well, first of all, we can pull that square root out, and we have the 2 divided by the square root of 3. Now, if I multiply by the square root of 3 over 4, well, let me go ahead and write that. We'll put it back into fraction form. I can simplify that down a little bit, and then we'll just have this integral left without that square root of 3/4 sitting there. We'll put another multiply sign in. Okay, now the square root of 4 is 2. So those 2's will cancel, and then I have the square root on the top and bottom. These constants, if you multiply them together, you get 1. So that's not there. We don't have to write that. And I just have the integral of 1 over square root 1 minus u. Oh, that should be a squared. Let's see. Yes, forgot a squared there. Okay, if we didn't have that squared there, we don't need inverse trig functions. We can just use a substitution and our backwards power rule to do that antiderivative. But here we do have a squared, so the antiderivative is inverse sine of u plus c. And finally, we don't want to stop at u, so we'll plug in our square root of 4/3. I shouldn't have copied that quite yet. Let's see. I'll plug it in for you, and then we'll be finished. All right, so here is my here's my result. That's what I get if I integrate 2 over the square root of 3 minus 4x squared. And again, I think I'm going to use Scientific Workplace to make sure if I take the derivative of that, I do actually get what I want. And I'm going to be a little more confident this time, but I'll probably get shot down and it'll be in some other form, especially since all those constants are floating around. No, it actually did it exactly like we had it there. So the derivative of this does end up being the 2 divided by the square root of 3 minus 4x squared. Okay, so our answer is right here. Inverse sine square root of 4/3 times x plus c. Okay, we're going to look at one more example here, and then we'll call it a video. And this example involves a trick. Okay, so I just want to do this trick so that you've seen it before and you'll be more likely to be able to whip it out of your tool belt when you need it next time. And this is, it's going to be a definite integral. The trick doesn't have anything to do with the definite integral, but I haven't done any definite integrals, so I'll do a definite integral here. It's the integral from 0 to 1 of x squared minus 1 over x squared plus 1, okay, dx. And it's not immediately obvious that inverse trig functions are going to play a role here. The 1 over x squared, or excuse me, the x squared plus 1 on the denominator, that hints that possibly inverse tangent could be involved here. However, for the integral to be inverse tangent, we shouldn't have any x's up top, and we have an x squared minus 1. Now we can't use substitution because our x is squared up here. If this were just an x, okay, then the derivative of x squared plus 1 would just be 2x, and we could somehow get our x's to cancel, but that doesn't work here because we have an x squared. What we're going to do instead is a trick. So let's see, this integral, what I'm going to do is rewrite negative 1. And I'm going to rewrite it as plus 1 minus 2. Okay? And that's the trick, is knowing to do that. Why did I do that? Well, because it's going to work. You'll get the hang of this. I mean, we got an x squared plus 1 on the bottom. When we do it this way, I can break it up into 2 fractions, and then it will be it'll be easy to do either of those fractions. So I got myself a math mode here. Let's see. If I break this up into 2 fractions, then I have the integral from 0 to 1 of x squared plus 1 over x squared plus 1 minus 2 over x squared plus 1. Okay, and you technically don't need these parentheses, but I'm going to put them there just to be real clear that I'm integrating both of these terms. And what happens here? Well, I'm going to break this up into 2 integrals. So I'm going to use my copy and pasting again. And I'm going to paste it twice. Okay, so I got that integral, and then I subtract 2 times the integral from 0 to 1. And what I did was I pulled out that minus sign and pulled out that 2. So I'm going to just leave a 1 there. Subtract 2 times the integral from 0 to 1 of 1 over x squared plus 1. Okay, well notice that's just the integral of 1, that first one. So for the first one here, the antiderivative is going to be x. And then for the second one, the antiderivative is, excuse me, not 2x, it's 2 minus 2 times the antiderivative of 1 over x squared plus 1. And we know that that's inverse tangent. Okay, and I'm going to evaluate this. Let's see. I know I had problems at one point figuring out how to get Scientific Workplace to do this bar. Yeah, I don't really like that bar. Let's see. Is it like that? I thought there was a way to just not have it do any bar. Oh well, I'm not for sure here. Can I put this kind of a bracket here. It shouldn't be showing me that one, but it is. Okay, just forget it. So I don't know how to make Scientific Workplace to do the symbol where I have a vertical bar and put a 0 down here and a 1 up there. So I'm just going to enter in text and say evaluated from 0 to 1. Okay, so that means we have 1 minus 2 times inverse tangent of 1 minus, I'm going to put this in brackets here, minus what I get when I plug in 0. I get 0 minus 2 inverse tangent of 0. Okay, so that's 1 minus 2 times inverse tangent of 1. So inverse tangent of 1, if I scroll up here, let's see, inverse tangent of 1 is going to be between negative pi over 2 and pi over 2. And that's the angle in that range that gives me a tangent of 1. Now tangent's sine over cosine, so to have tangent equal to 1 means sine is equal to cosine. The top and bottom are the same, and that happens at pi over 4. So this is 2 times pi over 4, and 2 times pi over 4 reduces to pi over 2. So I'm going to put pi over 2 there. And then we have a minus 0, and inverse tangent of 0, I'll have a plus 2 times inverse tangent of 0. Again, tangent sine over cosine. So we want to know when that's 0. We want to know when sine is 0 in the interval between negative pi over 2 to pi over 2. And that happens at the angle 0. So inverse tangent of 0 is just 0. And we get 1 minus pi over 2. Okay. I really enjoy Calc 2. I think a lot of mathematics starts to tie together in Calc 2, and I start to see that in this problem. Notice that we started off with an integral of a rational function. Nothing there said trigonometry, nothing there said geometric, yet somehow we end up with the integral being equal to 1 minus pi over 2. I really think this is some beautiful mathematics. Okay, so that's all I have here today, and I will see you all on Tuesday. And as normal, you will have a homework due a few minutes before class on Tuesday, and that homework is at least as long as the last homework. So I really encourage you to get going on that early, especially so that you can either email me or ask for help on Monday. Okay, so have a good weekend.